Chapter 5, Section 7, Solving Quadratic Equations by Factoring. And there's a couple things we're going to go through first before we get to the actually solving these types of equations. One is this principle of zero products, and then we're going to factor basically and set up something that's going to use this zero product principle. And the other thing too is second degree equations that they have a second degree equations, what they're talking about, or the second degree expressions are ones that have one term, or the largest degree of any term is 2, and has to be at least 2. So these are called quadratic equations, and they're really, when we look at, we're going to look at one point in here what these look like on a graph paper, or graphically, what happens with these. That's what puts these into a category in themselves, and we'll talk about that a little bit too. So in a quadratic equation, first is an equation. Now we've got an equal sign, which gives us the ability to solve, or basically find out what variable will make this equation true. And then they show us this pattern, which could be a trinomial, but we might only have two terms, and we'll look at those too. So in order to solve quadratic equations, we need to develop a new principle. And like we've spent a lot of sections in this chapter and everything else really not talking about any kind of new concepts. We were just looking at strategies to use these tools that we have, and some patterns for factoring and all that kind of stuff, and we'll still use that stuff. But this is a new thing that we're going to do. This principle of zero products is the realization of, and actually a proof that we're going to use, or a law. I don't know if they went as far to call this a law, but if I have a product which is an answer to a multiplication, and that answer is equal to 0, the only way that this can happen, and they say true if and only if a, the one of the factors, a in this case, is equal to 0, or b is equal to 0, or both. Okay, so the only way I can get an answer that's equal to 0 from a multiplication is one of those things has to be 0. They both could be 0, but at least one of those things has to be 0. So if I have an equation like this, where I have two factors really here, these two binomials are factors, and I'm going to multiply those things together, and if it's equal to 0, I can take that principle and say then either this one, this x plus 3 has to equal 0, or this one, x minus 2 equals 0. And what I end up with is two solutions, or two possible solutions to my equation. And these two solutions are make these things true. So they really are a solution again. So we take the factors, put them equal to 0, and then solve for the variable x in this case. So in this case we get x is equal to negative 3. And if I put negative 3 back in the original, I'd get negative 3 plus 3 is 0. 0 times whatever happens in there is going to be 0. Okay? And this other one is x minus 2 equals 0. Solve that, x equals 2. Same thing, I'd get x plus 3 times 2 minus 2, which is 0. Doesn't matter what happens with that x plus 3. Or I could put them both in there, I get 0 times 0 is 0. And that's what they're doing here, is basically showing the check that we do have, in this case, we have two solutions to this type of equation. And so if I have this one, notice that these are fully factored, or we have prime factored these things. If it started with a polynomial first, notice that they're cannot be factored any further. If you go back to last section we talked about. Well, here I have three factors. Well, and 3 or a constant is 1. So the only things I can't have a variable in here is these two here. So I set those equal to 0 using that principle of 0. I solve for the variable. In this case, I'd get 5x plus 1 equals 0, add a negative 1 to both sides, take 1/5 times both sides. I get x is equal to negative 1/5. Here I get x minus 7 equals 0, so x is 7. So I get these two solutions, and then I should check those. I go back to the original, check to make sure that I get a truth at the end, that 0 really is equal to 0, and so on. So the solutions here are negative 1/5 and 7. Here's another example. We got 7t times the quantity t minus 5. I'd set each one of these equal to 0, and that's what they're doing here. They basically take the constant out, and I could say 7t equals 0, so t would equal 0 too. If you want, you'd end up with 0 divided by 7, or 1/7 times 0, 0. And here I get 5. You'll see patterns here. When you have a factor which has just the variable in it, and there's no addition, there's no terms in that, it's pretty easy to say, hey, then it's 0. Okay? And the check, they just don't show this time. Okay? So what we're going to do is we're going to take this trinomial in this case. To be able to solve these things, we need to get factors or parts of a multiplication that's equal to 0, right? So the product is equal to 0. So what we do is we take this trinomial. We're going to use the things that we did. We went through that A, B, C, D strategy on factoring. So I look for common factors first, and there's no common factor. And then I have 3 terms, so I look for a perfect square trinomial. In this case, it's not. And then I factor with either grouping or FOIL. I would probably FOIL this one. That's pretty simple to FOIL. I look for factors of 6 that add up to 5. And so I end up with this factoring of the quantity x plus 2 times the quantity x plus 3 will equal 0. Well, for this principle of 0 products, then I can say, hey, this factor has to be 0, or this factor has to be 0. So I get x is equal to negative 2, or x is equal to negative 3. And then I check that back in the original and do that. And if I check this and it doesn't work, I've probably where you've made the error is in factoring. Factoring is usually the tougher part of this. Hopefully you're doing your math correctly. But definitely check these things. In fact, especially when we get more complex, checking is much less work, and definitely worth it to make sure that you're on the right track. Here's another example. I have x squared plus 7x equals 0. Again, if we go through our strategies on factoring, first we look for common factors, which in this case is x. So I get x times x plus 7 equals 0. Well, then these are factors, right? Am I done factoring? Yeah. You go through the C. Is there anything more I can factor? And then there's no. And then I would, I can check the factoring here. Maybe sometimes I'd skip my factor. I'm going to check my work here by checking for solutions. In fact, that is a better check. So I would say, this is the way it factors. So x is equal to 0, or x plus 7 has to be equal to 0. So I solve that and I get x is negative 7. And they don't show the check. But I put negative 7 in here. 0, I'd look at it and go, well, that's pretty easy. 0 squared 0, 7 times 0 is 0. 0 plus 0 is 0. That's an easy check. Probably negative 7, I better make sure, right? So I get negative 7 squared is 49. Again, I've said in prior classes, and all the classes I talk about, negatives are a big deal. This is really a parentheses around the negative 7 squared, which means negative 7 times negative 7, which is positive 49. Here I get 7 times negative 7, which is a negative 49. So that check basically is 49 plus negative 49. Does that equal 0? Yes. So that's a proper or a valid solution. Now, caution, we must have 0 on one side of the equation for this principle of zero products to be used. Get all non-zero terms on one side or the other. You know, usually cautions we've looked at are usually about common mistakes. But really, this is just how do I apply this principle? I got to make sure that I'm going to have a product equal to 0. So they're going to show us some examples here where I like this one on A, I have x squared minus 8x equals negative 16. Now I could start factoring and those kinds of things, but I'm going to have a problem because it's really not equal to 0. So I want to get it equal to 0 before I factor. And so what they do is they add a positive 16 to both sides, and I'd end up with this trinomial now equal to 0. So then I factor that, and this is a perfect square trinomial, and I do that. Okay. So in this case, our x value is the same number. So when we have a situation like this where I could actually do them both, or I would probably write this as x minus 4 the quantity squared, right? It's a factor twice. Then I just need to solve for the one, say how do I make that 0? X minus 4 is equal to 0, and solve that, you get 4. So in this case we actually have exactly one solution to this quadratic. The other type here, I have 4t squared equal to 25. Same procedure. I need to get, I need factors to work. These factors, or the product, which means answer to the multiplication, has to equal 0 before I can use that 0 principle. So it's kind of like I solve this original equation for 0. In other words, how do I make this 0? And so I add a negative 25 to both sides, and I get 4t squared minus 25 equals 0. Then I do my ABCD of factoring. I look for common factors, which there's not in this case. And then I have two terms, so I'm not going to check for trinomial stuff. I'm going to look for difference of squares, or if I have cubed things, I can have sum and difference of cubes. So in this case, I have a difference of squared. 4t squared is really 2t to the 2 power, and 25 is 5 squared. So there's my terms when I factor using difference of squares is 2t minus 5, the quantity times the quantity 2t plus 5 equals 0. So now I have a multiplication equal to 0. So I have to make each one of these factors equal to 0 and find out what the t, or the variable, will be in this case. So here you'd solve this equation, 2t minus 5 equals 0, add 5 to both sides, take 1/2 times both sides, and you get t equals 5/2. Here I take a negative 5, I add to both sides, I get 2t equals negative 5, take 1/2 times both sides, and I get a negative 5/2. So I have these two solutions of 5/2 and negative 5s. And I would check that back into the original right here. Not into my factoring, but check this. I put 5/2 in here, and I'd get, if I square 5/2, I get 25 over 4, which then is 4 times something over 4 is just going to be the numerator, right? 25 equals 25. If I square this, again, remember that order of operations, I'm going to have negative 5/2 times negative 5/2, which is a positive 25 over 4, and I end up with the same 25 is equal to 25. So those are truly solutions. Truly for solutions is kind of weird to say because solutions make things true, right? So now in this case where we have it factored, but it's equal to 9, we might want to be really tempted to say, hey, it's factored. They already factored it for me. Well, it won't work unless it's equal to 0. So I have to multiply this out, get the trinomial in this case, and then take care of my zero issue. So the first part of this is, hey, this product isn't equal to 0, it's equal to 9. I have an infinity of ways that I can multiply two numbers together and get 9. So I have no ability to find a solution when I have a 9 over here. I have to have a 0 over there. Well, and also I need to deal with things being addable in a sense, because I'm going to add a negative 9 to both sides. So I want to convert this into an addition by multiplying this out, which I get this trinomial of 2x squared plus 5x minus 3. And now this is back to kind of where we started before. I said, well, let's get this equal to 0, and I'm going to add negative 9 to both sides. So now I have a trinomial of 2x squared plus 5x minus 12 all equal to 0. Hey, if I factor this, if I can find factors of this, those factors will multiply to a product of 0. Now I got the ability to get a solution. So they factor this, and go through your factoring strategies, and they get these two factors. They solve for x, and you get these two solutions. Now, notice that they don't go back to this and check or anywhere else. They go right back to the original problem and check those solutions. Okay? And they do work. Now let's look at this concept. This is a part where graphing, we went through in earlier in the book, in probably a prior course if you took 93 and or other algebra courses, we've done a lot of work on graphing things. And they're going to show us some things about quadratic equations on what they really look like, and that's what they're setting up here. If I have a coordinate plane, now I have two variables to represent this coordinate plane. So they say y equals ax squared plus bx plus c of this type. We end up with graphs that are shaped like these U's. They're called parabolas. And they're showing us all the different things that can happen with these parabolas. Well, when I have no x-intercept, in other words, I have no place in this graph where I have a 0 for x. If I think of all these ordered pairs here on this parabola, there's no ordered pair on here where x is ever going to be equal to 0. So in other words, there's no real solution to this parabola here. And there are possibilities, and we're going to run into some, where I could go through this factoring and all those kind of things, and I just can't find a solution. And this would be in the case where I have like a trinomial that I can't factor. That fits into that sometimes. Now, you could have the parabolas in this case, these fall into the same deal. In some of the things we've solved in the examples, we were talking about having two solutions. Well, that would be a graph that would look like this or this, where the solutions are the zeros for the x, right? These ordered pairs on the x-axis, I'm saying x, zeros for x, I mean zeros for y, are every point on the x-axis, the y is 0, right? And that's what I need to do, is replace this y with 0. The only way I can do that is that there are points on this x-axis, and then I have that ability to factor. Well, here's what something looks like when I have two solutions. I actually have 2 points, 2 different values for x that will make the y go to 0. And it could look like this too. Now there's also the possibility that we have exactly one solution. Like one of the examples, we just had one solution. That means that the vertex, this point right here at the bottom of our parabola, or top of the parabola in this case, notice these go for infinity, so it has a limit, or basically a point that is the highest point in this case, or like this one here is the lowest point. There's actually one point that occurs at. Well, when that one point is on the x-axis, then we have exactly one solution. So these graphs, I could ask questions like that. How many solutions are to a graph like this? Well, in this case, there are none. There's not zero is a solution. It's just there's no solutions. There's no occurrence of it being equal to zero, this trinomial. And here it'd be 2, 2, and 1. Those are the four, actually three things that can happen, right? You have none, 2, or 1. So example 8, it says find the x-intercepts. And I go back to the graphing. In other words, what happens on every, again, I can't emphasize this enough. It gets kind of lost in the translation a lot of times. If I'm looking for something where it crosses the x-axis, what am I saying is really where is y equal to 0, right? Every point on this x-axis, the y coordinate or the vertical change coordinate, the second coordinate in the ordered pair, is 0. So to find this graph, I can say, hey, I got this, right? Here's a picture of it. I do have two of them, it looks like, for sure. And then I would basically say, well, I would make the y equal to 0. That would be looking for these 2 points. So you put 0 equals x squared minus 4x minus 5. And now I'm back to using the 0 principle. And I can find my 2 solutions. And they're actually ordered pairs with the y coordinate being 0 here. Okay? So that's a good tie-in to how graphing works. And obviously, if you're going to try to graph a parabola, those would be interesting points to graph on there is your x-intercepts. And not having an x-intercept will tell you a lot of things and those kind of things, which is then they're kind of tying into your graphing calculator, which will graph a lot of this stuff for you. So there's section 7, and I'll talk to you later.